Hi everyone. Today we're going to talk about the alternating series test. So this is going to be a new test for us in terms of determining whether or not a series is converging or diverging. But before we get to that, let's do a little bit of review. Let's take a look at a few other series, and we're just going to try to determine whether each infinite series will converge or diverge. And of course, we have to justify our answer somehow. So for A, we have the terms -3 plus 1 minus a third plus a ninth minus 1/27th plus 1/81st, etc., etc. And hopefully we can look at these terms and recognize that this series is geometric with an R value of -1/3. And so as long as the absolute value of R is less than 1, we know then that this geometric series will converge. Excellent. Let's keep going. B. Let's take a look at the terms. 1 plus a half plus a third plus a fourth plus a fifth. I'm hoping you recognize this series. This is kind of a famous series we've talked about a few times now. First off, let's just write it in sigma notation. Not something we have to do, but just something that's good to practice, right? Sigma n equals 1 to infinity of 1 over n. And I'm hoping we recognize that this is the harmonic series, which diverges by the p-test because here p is equal to 1. Now, if we take a look at C, C has the same absolute value as B, right? Looking at the absolute value of the individual terms, but here we have an alternating series, right? We start with a positive term, negative, etc. We're going to come back to C in a moment. Let's go down to D, because that one's actually a little easier for us to tackle. Even though this is also an alternating series, I don't have to use anything new to determine whether or not this will converge or diverge because we have learned our old friend, the nth term test. The limit of the sequence here as n goes to infinity is not going to be 0. And if we recall, right, this has to be a prerequisite for convergence. And so because the terms themselves are not approaching 0, right, we know that this series will diverge. Okay, so what about C then, right? This one is alternating, and so this is going to bring us to something new here, but it also involves what we did on D, which is the nth term test. So let's talk about our new test for today, the alternating series test. So here's what it says. If I have some series, right, and so I'm writing it out here in sigma notation, we're saying this starts at n equals 1 to infinity. It doesn't have to start off at n equals 1. I just have some sequence, right? A sub n, the terms are a sub 1 plus a sub 2 plus a sub 3, etc. This series will converge if all three conditions are met. So the first condition, this is called the alternating series test, right? The series must alternate in signs. Doesn't matter if it starts positive, right, and then goes negative, or if it goes negative, positive, etc. The series has to alternate, which makes sense given, again, the name of the test. The second thing that has to be true is that the absolute value of a sub n has to be greater than or equal to the absolute value of a sub n plus 1 for all n after a certain point. So just a quick little future tip. I remember learning this in college. A shorthand for the phrase for all is an upside down A. Okay. So let's talk about what this means, right? This is really just a fancy way of saying that the terms in your series have to eventually start getting smaller. So if I go back and take a look at C here, right? I start off with 1. Now we're going to ignore the alternating signs for this part. We're just going to take a look at the absolute value, right? 1/2 is smaller than 1. 1/3 is smaller than a half. 1/4 is smaller than a third. 1/5 smaller than 1/4. The terms have to be getting smaller. And now it says after a certain point, meaning let's say the first 2 or 3 terms, the terms don't get smaller, right? Well, if they start getting smaller after that, let's say n equals 3 or n equals 4 term, then it still works, right? At some point, the terms have to start getting smaller, and we'll talk about how to deal with that. And then the last thing is basically the nth term test, right? Again, the prerequisite for convergence is that the terms in the sequence have to be going to 0. Okay? If you can show that these three conditions are being met, then you know your series will converge. And that's the alternating series test. So let's go ahead and try to apply this for our series back on part C. So first thing, again, just to kind of practice, right? Let's try to write this in sigma notation. So if you want to pause the video and try that yourself, I think that would be a good idea. Otherwise, we're going to go ahead and do it right now. So this is sigma from 1 to infinity. The denominator here, right? I can think of this 1 as being 1 over 1 if it helps, right? 1, 2, 3, 4, 5, n equals 1. So n is my denominator. And now the alternating part with the numerator, starting with a positive 1, because n equals 1, I'll go negative 1 to the n plus 1 power. Okay, so let's try to apply the alternating series test to this. So step 1, does the series alternate? Yes, it does, right? And there really isn't a lot of work you have to show for that. It's just write out a few terms, right? And then show me if they alternate or not. Right? And, again, you don't have to prove this infinitely or anything like that, right? If you show me a few terms, that's really all I'm looking for, okay? The trickiest part of the alternating series test really is going to be number 2, okay? Because you have to establish what the n value is that makes this inequality true. So if I apply that here, right, if I go ahead and take the absolute value. Now, the nice thing with this one is if I take the absolute value, I can basically just ignore the alternating part. And so the numerators are all just 1. And so 1 over n, right, is that greater than or equal to 1 over n plus 1? Yes, that is true. And then one thing I'm going to add to this is that this is true for all n values greater than 0. Right? Because starting at n equals 1, I know that this is true, that the terms immediately start decreasing. Okay? And now the last thing is just basically, again, the nth term test, right? What is the limit as n approaches infinity of my a sub n? And remember, a sub n is just whatever you have in the sigma, right? And for this one, if I go ahead and apply it here, right, this does get me 0, right? The denominator grows infinitely. The numerator is bouncing between 1 and negative 1. So this is going to be approaching 0, okay? And so if I show all three of those things, I can go ahead and say that this series converges by the alternating series test, or AST for short. And so that's the whole idea here, right? Now it's just a matter of, can I apply this to a given series? So let's go ahead and practice a little bit more with this. So just at the bottom here, I'm going to go ahead and write 2 different series. And this might be a good thing for you if you want to pause the video right now and try to show these 2 on your own, whether they converge or diverge. So, with the alternating series test, that is only a test for convergence. Right? If you show those 3 things, if any one of them is not true, does it show divergence? Yeah, it's not really a test for divergence, right? The same way that, if you have a geometric series and the absolute value of r is bigger than 1, it diverges, right? If you don't meet the conditions for the alternating series test, it doesn't guarantee that your sequence will diverge, okay? So we have to show divergence in another way. All right. So again, if you want to pause, try these on your own, that's fine. Otherwise, we're going to take a look at these together. So number 1, from 1 to infinity, we have negative 1 to the n plus 1 power times n squared over 3n squared minus 5. So I can see from this part, the negative 1 to the n plus 1, this is going to be an alternating series, okay? And so, is this going to converge or diverge? Let's see if we can figure it out. So first thing I did over here is I just rewrote the series. You don't have to do that. And one thing that's kind of nice to do here is if you actually start with number 3 sometimes, right? That can be a quick way to show that something does diverge, because if number 3 is not true, then you do know that your series will diverge, because that alone is the nth term test, right? And so if I go ahead and I apply that here, and I take a look at this and I go, okay, I have n squared on the top, I have 3n squared on the bottom. Remember, n is going to infinity, so minus 5 doesn't really matter here. Nth term test gives me that this is 1/3. So if that specific condition, the number 3 from alternating series test, is not met, that's just the nth term test. That's what you're using to show divergence. Okay? So this diverges by the nth term test. All right. Let's try to do the same thing for number 2 here. Okay, so again, -1 to the n plus 1, so I know this is going to alternate, times quantity n plus 4 over 3n squared minus 5. And let's take a look at this series. So first thing I did over here is I just copied and pasted the series itself again. And it's not a bad idea for when you think the nth term test will apply. You have to figure out when the terms start decreasing. So it's not a bad idea to write out a few of the first terms, which is what I did here. Okay, so when n is 1, right, we can go ahead and plug 1 in here and simplify. We get -5/2. Now, when I plug n is 2 into here, right, do I get a negative, or is that a typo? Negative. No, yeah, that's a negative. Okay. Yeah, this term is also negative. Sorry, I forgot that when we plug n equals 1 into this, the denominator is negative, which is why the first term was negative as well. So when I plug in n equals 2, I get a negative again. So the series doesn't start off alternating. That's okay, because when I plug in n equals 3, right, I get a positive. When I do n equals 4, I would get a negative. So it does start to alternate eventually. It doesn't matter that the first term doesn't start off alternating the series right away. So that's okay, right? Again, it's kind of the same idea with bullet point number 2 here, right? The terms have to get smaller eventually. The series has to start alternating eventually. It's the same idea, right? Because, I can basically say ignore the -5/2. Is the rest of this an alternating series? Yes, it is. So, does this series alternate? Yes, it will, right? After the first term, this series will alternate, and that's okay. Now, for the second condition, are the terms getting smaller, right? So, I'm going to check plugging in a sub n versus a sub n plus 1. And so that's what I've written here. Absolute value of the a sub n term. So again, because it's absolute value, I can ignore the -1 to the n plus 1 part of this. Okay. And now, is absolute value of a sub n greater than absolute value of a sub n plus 1? Yes, they are. And again, this is why it's good to take a look at my series, right? So if I just start taking the absolute value of these terms, is 5/2 greater than 6/7? Yes, it is. Is 6/7 greater than 7/22? Yes, it is. So I know that the terms are getting smaller right away, starting whenever n is greater than 0. And I'm writing it like this because my series starts at n equals 1. You don't have to write it like this. You could say n is greater than or equal to 1, right? That also works. Okay, so however you feel comfortable writing that is fine. You just have to make sure that it's true for whatever condition you give it, right? So, let's say my second term was not 6/7. Let's say it was 6/2, right? And then this would not be true, right? Then I would have to specify that these terms are only decreasing when n is greater than 1. Okay, so we have to keep this type of thing in mind. So again, it doesn't apply here. We can say just n is greater than 0 or n is greater than or equal to 1. And then the last thing is, again, just the nth term test, right? And so, again, I can, -1 to the n plus 1, I can basically ignore that part of it, right? And just say limit as n approaches infinity. I can go ahead and add it in, right? It should be there. but it doesn't really make a difference when we're talking about a limit as n goes to infinity, right? This part isn't really doing much, which is why I didn't originally have it. Now I need parentheses, though, around n plus 4. Okay. But we can take a look at this, right? Take a look at the degrees, n to the first over n squared, right? And so this is going to go to 0. So nth term test is satisfied. And so because all three conditions are met, this series will converge by the alternating series test. Okay, so last thing I want to bring in here is just the idea that, how do you know when to do this, right? So an alternating series, right, you can typically tell that by the terms or when you have it in sigma notation. But remember, the main idea here is we're trying to avoid doing a ton of work with things like the ratio test, right? And for stuff like this, could I have applied the alternating series test to example A? Absolutely. But geometric series test, right, just looking at the R value is faster. Okay, so it's really just about, trying to be expedient with our work. Okay, so that's all we have for today, and I will see you next time.